down by the financial crisis because I had just gotten an NSF grant in January of 2008. The grant I wrote was to work on this, to work on cognitive imprecision. And then, of course, in 2008, the world fell apart. And I spent the next several years writing a lot about problems of financial intermediation causing macroeconomic problems because it seemed like an important thing to be working on. And so it set this back several years. But after a few years, from sort of 2012 on, I started working a lot on this again. But it was more that the financial crisis impeded my making faster progress than being the thing that made it happen.
Yeah, and lots are happening now on this, no? In macro, I mean, many people are working, so it seems that
I think that's right. I think it is something of growing interest, and I think probably the financial crisis did contribute to that. I mean, probably contributed to the degree to which there is broader openness to the idea that cognitive imperfections might actually be important, particularly for macroeconomics.
Yeah, it's almost, I mean, it's kind of amazing how a crisis can bring in, completely new, very productive research in some sense. If you think about
macroeconomics
macro
has always been a field like that. I think a lot of the progress in the field gets pushed to the fore by economic crises of different kinds. I mean, the Great Depression, which led to the rise both of Keynesian economics, but also macroeconomic modeling, I think. All of macroeconomic modeling, Tinbergen's work and the Coles Commission and all of that came out of a response to the Depression. I think, and the inflation worldwide in the 1970s spurred lots of new thinking in macroeconomics and lots of methodological innovations. And sort of we need, it's, of course, the world doesn't need them, but the field of macroeconomics makes faster progress when we have interesting crises occurring somewhere in the world.
Because when I was doing my PhD, I worked on growth, of course, not directly in macro and business cycles, but then thinking out of in any framework which is not rational expectation was kind of unthinkable. And then gradually the world has changed, and I think it's a great move forward, and to have a sort of a formal model, not to go back to this kind of ad hoc adaptive expectation. So this is kind of fascinating stuff. So I was just so glad that you would be talking about this because it's just absolutely, I find it very, very fascinating. I mean, the micro behavioral economics has been there for a long time, but application of that to macro is something that it's quite...
is developing a little more recently.
So Shomendu, how are we doing in terms of time? 2 minutes, is it?
2 minutes to go, and then we can begin.
And people are already joining in?
Yeah.
So Michael, this is in webinar mode because this is basically we expect a large audience, so it's not going to be a meeting mode. So except for some people who are right there in those boxes, others are going to be in the audience, but they will be muted. So during your talk, I'm not going to unmute them, but at the end, if they have questions, so I'm going to ask them to have if they have clarifications, then I'm asking them to use the chat box. After your talk, if there's time, then I'll probably enable more direct interaction that might be more interesting. But how is it going for teaching in Colombia? Do you teach? I mean, are you teaching? Where you teach?
Yes, well, the term has just finished recently, but we were back to classes in person this fall.
I see. So it will be in person from this.
Yes.
Because that's much better. Except that hopefully the pandemic will not act up again. Let's see.
That's what I'm hoping. It's I keep hoping that, and it keeps not quite happening. But let's hope 2022 is better.
Yes, I mean, you talk about persistence. I mean, this is really, this just wouldn't go away. It's amazing how it's coming up in different forms. Okay, should we start, Somendu? or give some more minutes, 2 more minutes?
1 2 more minutes, maybe some participants will join more.
All right. So this would be a sort of a very hectic for you, huh, Michael? I mean, tonight and then again early tomorrow morning. So
right, because of course it's night here. I mean, it's
yes, yeah. But thank you very much for agreeing to do this. This is just, so wonderful for our researchers and our, research. And I think that's one good effect of the pandemic, that it has been, the connecting to the,
That's right. No, it's easier to speak in more parts of the world. That's been one
less
thing we've learned how to do that we didn't know how to do before.
I think we can begin.
Yeah, let's start. Yeah. So then others will, I know that it's definitely in the morning, they, after 10-15 minutes, they are trickling in. So there's no point waiting. Okay, welcome everyone to the second day of the Winter School Conference, which is jointly organized by the Delhi School of Economics and the Econometric Society. And it's my pleasure and privilege to introduce today's speaker to you, Professor Michael Udford, who is the John Betts Clark Professor of Political Economy at Columbia University. I really don't think Michael needs an introduction to this audience. Anybody who has done, taken a course on monetary economics would be familiar with his book on interest and prices, and the foundation of theory of monetary policy, which is a standard text in monetary economics. And anybody who has done any kind of research in either macro or monetary policy must have glanced through those volumes of handbook volumes on macroeconomics and monetary economics, which are co-edited by Michael. But what I personally found absolutely fascinating about Michael's work, recent work, is basically this recent research, not so research for him, but this recent research in the field on behavioral macroeconomics. And Michael basically explores the ideas of bounded rationality and imprecise cognition, how that impacts, economic decision making of the agents, and of course, there are, implications for policy and in particular monetary policy and so on. So Michael's lecture, there are 3 lectures in this series, and all 3 of them are related to this theme. So I'm not going to take any more of your time. I'm very excited, and I'm sure all of you are also very excited to learn more about this very, very interesting research arena, which has opened up as I was chatting to, or at least become more popular after the global financial crisis. So before I hand it over to Michael, just a few housekeeping rules. One is that because this is a webinar and we expect a large audience, we won't be able to, unmute you during the talk. So basically, if you have any questions and during the talk, I'll, expect you to just write clarificatory questions. So write them in the chat box, and I'm going to convey them to Michael at an appropriate time. But if you have more substantive comments, questions, anything else, then at the end, if we have time, then I'm going to, take them up and directly, hopefully I'll be able to unmute you so that you can directly ask your question to Michael. Also, I want to tell you that after all the 3 lectures are over, there's a breakout session that's today, India Standard Time, 10:15 p.m. When you can, all of you, if you register for that, then you can directly interact with Michael and discuss whatever the interesting ideas that you're going to listen to now. So over to you, Michael.
Hey, thank you very much for that introduction. I'm very pleased to be invited to give these lectures. I'm sorry not to be able to be there to do it and to actually get to meet some of you. But I'm happy to be invited to speak. The topic of these lectures is going to be the importance for economic modeling of taking into account imprecision in cognition. So specifically, I want to argue that we need to model people's choices as responding only in an imprecise way to the precise details of the situation that they're in. So as you know, the standard method in economic modeling has been rational choice theory, which seeks to explain behavior as being optimal from the standpoint of some coherent objective that each decision maker has, assuming a correct understanding of the exact properties of the choices that are available to them. And often this is so much taken for granted that it isn't even emphasized, although I've put it in bold here, that it's standard to assume that people are responding to exactly what the true properties are of the choices that are available to them. Instead, I want to talk about an approach that's going to allow choice to be based on an imprecise subjective representation of the features of the situation that the decision maker is in. And the idea here is that the degree of precision of this internal representation is going to depend on how much attention the decision maker is paying to particular features of the situation they're in. Greater precision would require greater attention, which is going to require more information processing resources. And the spirit of this is going to be assumed that these resources are not in unbounded supply and that we need to take that into account. The thing I'm going to be talking about in the lectures is not so much how to understand these constraints on the information processing resources, but how to modify economic models to take into account the idea that the internal representations that decisions are based on are in fact necessarily imprecise. So I want to start by talking about what kind of features of observable aspects of choice behavior provide evidence of the kind of cognitive imprecision that I'm talking about and that we want then to be able to have our models be consistent with. The first observation, maybe the simplest and most familiar one, is that choice behavior is often apparently random, conditional on a complete description of the options available to the decision maker. And one way that one can see this randomness is by having the same experimental subjects presented with exactly the same choice problems more than one time, not immediately after the last time they were asked, but after being asked about some other things, so they don't realize they were just asked the same question a little earlier in the same experimental session. And when one does this, often subjects give different answers rather than giving exactly the same answer when exactly the same choice options are presented to them on another occasion. This doesn't mean that observed choices have nothing to do, though, with the properties of the options that they're being presented with. What one observes is that choices seem to be probabilistic, but that the probabilities of different choices are what vary systematically with the characteristics of the options that are presented to the decision maker. So a classic example of this, to give you an idea of what I'm talking about, this is from a paper by Mosteller and Noji in the Journal of Political Economy back in 1951, one of the earliest laboratory experiments on people's behavior with respect to simple gambles. It was an attempt to experimentally estimate the von Neumann-Morgenstern utility functions to test whether von Neumann and Morgenstern's theory, published a few years before this, fit actual human behavior. This is a figure from that JPE paper illustrating the kind of data that the authors were collecting. And here they're plotting data for a set of experimental trials for one experimental subject and one class of decision problem that came up repeatedly during the experiment. In this particular class of decision problems, the subject is given the opportunity to pay 5 cents. If they pay the 5 cents, they get the outcome of a gamble. The gamble gives them some amount of money X with probability 1/2 and 0 with probability 1/2. The amount X is different on different trials, and it's the quantity on the horizontal axis. What's being plotted on the vertical axis is the percentage of the times for a given value of X that the subject accepted the gamble. And so what you see is an upward sloping curve. The circles are the data. They're connected by lines that interpolate between them. It looks like a nice increasing curve. So the bigger X is, the more likely the subject was to accept the gamble. The figure is illustrating how the authors proposed to calculate an indifference point by interpolating between these points, asking where on the vertical axis you went through exactly 50%. The thing I'm interested in is not where that indifference point is, but in pointing out that the behavior is probabilistic. These data are not consistent with the view that the subject knows how much they value each of these different simple lotteries. They have a definite valuation, they have precise access to that valuation, and they always choose predictably the thing that they value more. Instead, one sees that when X is 10%, sometimes they take the gamble and sometimes they don't. About 30% of the time they take it, about 70% of the time they don't. But there are many times when they do and many times when they don't. When it's 11 cents instead, now they take the gamble about 2/3 of the time, but about 1/3 of the time they don't. Okay, so one is seeing apparently random behavior when one has repeated presentations of exactly the same choice problem to exactly the same decision maker. Okay, another way of seeing this evidence that decisions seem to be based on an imprecise understanding what the decision maker is doing is that if you ask experimental subjects how certain they are of the decision they make, they'll often report that they're uncertain to different degrees. And an example of that from a recent paper by Ben Anke and Thomas Graeber from earlier this year, they have an interesting way of measuring this degree of subjective uncertainty. It's again, subjects are presented with a simple gamble. In this case, the subject has to state a monetary amount such that they would be indifferent between that certain amount and the lottery that's been described to them. And the wrinkle on the way Anke and Graeber do this is that they allow subjects to report an interval of values rather than a single number. So they can say two quantities A and B, they're supposed to report the two quantities such that they're certain that the lottery is worth between A and B to me. And what they find is that in most cases, the subjects don't put A and B as close together as possible, as they ought to if they knew exactly how much they valued a given lottery. Instead, they choose some non-trivial interval of values when they then feel more certain that the value belongs in that interval. Another source of evidence that can be interpreted as indicating imprecision in people's understanding of what to choose is the observation that people take time to make a decision. And it seems that if you measure the time taken to announce a decision, that they often take more time when choosing between two things that they value to a relatively similar extent. So one observes that when presented with a choice between two things where the subject values one of them a lot more than the other, they make a quick choice and a pretty predictable choice. But when the two things are closer to being similar in their values, then they take longer to make a decision. You can use measured response time then as a measure of the decision maker's cognitive uncertainty. If you do that, the conclusions you reach about how much uncertainty there is for different choice problems often line up well with what would be indicated by the degree of randomness of choice. So this is an example of that data taken from a paper by Ian Krybik and co-authors published back in 2010. This is an experiment where subjects choose between food items. They're presented with two food items. Then they are told whichever one they pick. There's a certain probability that that choice will be for real and they'll actually eat at the end of the experiment, the thing that they picked. In a first stage of the experiment, the subjects first rate the different food items according to how much they like each of them, just considered individually. So what's being plotted here in the panel on the left, for different pairs of food items, on the horizontal axis is the difference in the relative value of the item on the right relative to the item on the left, according to the subject's own rating of the items in the first stage of the experiment. On the vertical axis, the fraction of the time that they pick the item on the right as opposed to the item on the left. Again, one sees what looks like probabilistic choice as a function of the relative value, although it's a nice, smoothly increasing curve. So that's like what I showed you from Mosteller and Noji. The interesting thing here now is that on the right panel for the same choices. On the horizontal axis, again, is the difference in reported value between the item on the right and the item on the left. On the vertical axis is the average time it takes the subject to make their decision in milliseconds. And what one sees is that in the cases where the responses are more random, which is when the relative value is not too different from zero, slightly positive, slightly negative, so the probability of choosing the thing on the right is not too much bigger or smaller than 50%. For those same choices, choices are also slowest on average. Choices are faster when the value difference is bigger in either direction. That's when choice is also less random. Okay, so that also seems to be a measure of cognitive uncertainty. What we would like to be able to do is to introduce this kind of imprecision into not just qualitative, but actual quantitative models of decision making that we can fit to data like the ones I've been showing you. So the fact that choice is, or at least appears to have a stochastic element, is not a recent observation. I showed you a figure from a 1951 paper. In fact, experimental economists and other empirical microeconomists have been aware of this for decades. And there's a fairly common approach for introducing randomness of choice into economic modeling that's been around for more than 50 years. This most common approach assumes that people do have a precise value that they can assign to any given option. This value is a deterministic function of the objective features of that option, and that precise value is an input to the decision process. But this kind of model assumes that instead of choosing the higher valued option with perfect certainty, they choose randomly as a function of the difference between the values of the two items. So a common example of a stochastic choice rule to implement that sort of thing quantitatively in a type of model that's been estimated on a lot of data sets assumes this thing that I'm calling a softmax function. So there's a value v sub I and v sub j, the values that are assigned by this decision maker to the two options I and j. Those are assumed to be definite numbers that are inputs to this choice rule. But instead of definitely picking one of them or the other, if vi and vj are not equal, there's a probability of choosing j over I that's a function of vi and vj, and it's this function, this softmax function I've written here. It has a parameter theta, a positive number, the so-called temperature parameter, that determines how random the choice is. The bigger the value of theta, the more random the choice is for a given difference between vi and vj. And you can observe that that function is a continuously increasing function of the extent to which vi is bigger than vj. It's in fact just a function of the difference between vj and vi. It's a flatter function the bigger the temperature parameter theta is. We can interpret this as a model that assumes that people don't have problems recognizing what the options are, exactly what their characteristics are, therefore what their values to them are, but that there's random noise in the process of comparison of the two values to one another. So there's randomness, but the randomness is being modeled as only relating to problems of comparing vi and vj and recognizing exactly how much one of them is bigger than the other. Some examples of particular noisy comparison processes that might be motivating that formula. The one that's the most familiar in the microeconometrics literature is the additive random utility model that Dan McFadden's Nobel Prize winning work in econometrics was based on. Here the idea is that instead of comparing vi and vj precisely, the decision process is going to take vi and vj, add a random term to each of them to produce these quantities v tilde I and v tilde j, and then on a given trial, for given draws of epsilon I and epsilon j, the decision maker will choose the option with the larger value of v tilde. If these additive random terms, epsilon I and epsilon j, are two independent draws from a Gumbel distribution with a scale parameter of theta, then you can calculate the probability that v tilde j will be bigger than v tilde I, which is then the probability that j is going to be chosen over I, and it's going to be exactly that softmax formula on the previous slide as a function of what the Vj and the Vi are. So that would motivate that stochastic choice rule. Another example, though, that's been very popular in the mathematical psychology literature and the computational neuroscience literature is a model that's called the drift diffusion model. Here, the model postulates an internal decision variable in the mind of the decision maker that's evolving according to a Brownian motion. It hypothesizes that this Brownian motion has a drift proportional to the difference in the values of the two options. And the decision for one option or the other is made when this Brownian motion first reaches one or the other of two boundaries. So there's an upper boundary and a lower boundary, and if it reaches the upper boundary first, you pick J. If it reaches the lower boundary first, you pick I. You can calculate the probability that this random walk hits the upper boundary first rather than the lower boundary, and that's going to be a function of the drift, which is a function of Vj minus Vi, and it'll in fact be exactly that softmax formula. The theta is going to depend on the constant of proportionality between the drift and the value difference. It also depends on how far the two boundaries are from the starting point. An interesting thing about this interpretation of the softmax model of choice is that this is a model that can also make quantitative predictions about how long it will take to make different decisions. You can calculate the predicted mean time to hit one of the boundaries as a function of Vj minus Vi, and the model predicts an inverted U-shaped function of exactly the kind in that Kreibich et al. Experiment. In fact, back in this figure, the circles are fits of that model that I just described to these data. The same parameters fit the pattern on the left and the pattern on the right, and so we can simultaneously explain the randomness of choice and the variability in the amount of time involved in making different decisions. Okay, a third example of an interpretation of the softmax function is a model where one hypothesizes that it's costly to control your response more precisely, even given what you know about the value of the different options. And this is an idea Stahl proposed in a paper back in 1990. In Stahl's version of this model of control costs, it's assumed that if you have two possible actions, each one has an expected value to the decision maker of Vi and Vj. Those are known to the decision maker. It's assumed that the decision maker doesn't pick a definite action, but instead picks a probability distribution over the possible actions. They pick this probability distribution to maximize an objective, the first term of which is the expected value to them of what they get from the random action, but there's a second term that depends on how random the action is. So the first term there, Pi Vi plus Pj Vj, that's the expected value if the probabilities of choice are Pi and Pj. The second term is a quantity theta multiplying the entropy of the response distribution. This is a measure of how random the response distribution is. It's bigger if choices are more random, and that increases the objective. So this captures the idea that it costs the decision maker something to make their choices less random. If you solve the first order conditions for maximizing that objective, you get a probability distribution which has a probability of picking Vi and Vj, exactly the one given by the softmax formula, where the theta in the softmax formula is exactly the theta in this problem. So that's yet another interpretation of that popular softmax model. What I want to mainly talk about in the lecture is not the difference between those different models of comparison noise, but a difference which I think is more interesting between all of those models, which model the noise in choice as only being related to comparison noise, and another kind of model that I want to talk about. And this is a contrast that I'm going to draw between what's sometimes called late noise in the decision process and early noise. The late noise models are illustrated by the three models that I was talking about, where there's no problem recognizing the options, their characteristics, valuing them. There's a definite value for each option. It's an input to the choice process. The noise comes in only at the end of this process when you have to compare the options and produce an actual response. The alternative that I want to talk about as a way of getting choice to be random is the hypothesis that perhaps the features defining the available options are themselves corrupted by noise at an early stage in the decision process, before the information about these different features are integrated, maybe even to come up with the assessments of the values of the individual options. So one could then have, in this view, random choice as a function of the objective features of the options that are presented to the subject. But one could get choice to be random even under the hypothesis that the decision rule of the decision maker is making optimal choices conditional on the choice having to be based on this noisy representation of what the decision problem is. So it could be optimal choice given the noisy representation. That means you could be picking with certainty the thing that has the higher estimated value if those value estimates are optimal estimates conditional on the estimates having to be based on a noisy representation of the problem. If you ask where I come up with that idea as a proposal, this is in fact the most common interpretation of randomness of people's judgments when they're making perceptual comparisons as opposed to choosing whether they want to get one thing or another. So there are many experiments in perceptual psychology where subjects have to compare the brightness of one light to the brightness of another light, the speed of one thing to the speed of another thing, the size, the length of a line to the length of another line, and so on. One observes that subjects' responses are random, or often random, as a function of the objective characteristics of the stimuli that are shown to them. And this is commonly interpreted in psychology in terms of quantitative models that assume the decisions are being based on noisy sensory information about the true characteristics of the thing in the environment. And if you ask why do psychologists believe that, there's fairly direct evidence that early stages of processing of sensory information in the nervous system involve demonstrable randomness. One knows a lot about which parts of the brain and which parts of other parts of the nervous system, like the retina and the optic nerve and so on, are involved in processing sensory information. One can measure the randomness of this processing. And there are interesting experiments that even show that the degree of randomness in the case of different stimuli of the neural processing can account for differing degrees of randomness in the subject's judgments. So that's a common line of explanation in modeling perception. And in that literature, some of the models do model the decision process as an optimal decision process conditional on the noisy sensory data, which is the line of discussion I'm going to be pursuing in this lecture. Now, you might ask, why would I talk about this as a possible model of economic decisions, like the choices with regard to lotteries that I was talking about earlier? You might say, well, perception, we can believe that the sense organs are noisy. We know that the available data about perceptual features of our environment involves noise in the neural processing. Is that relevant to economic decisions where perhaps the data are presented symbolically, as in, say, Mosteller and Noji's experiment? They were told numbers. They're told these numbers with number symbols, and surely the subject hears the word 11 cents quite precisely because it's a very symbol with a very precise meaning. The early noise that I'm talking about under this other hypothesis doesn't have to be interpreted as actual perceptual noise. It's something that could exist even in the case of data that are when originally presented to the subject, they are accurately perceived, say because they're presented with clear symbols and the subject does recognize what those number symbols are. Nonetheless, the data might then be recorded or retrieved with noise when that information is being integrated with other information to form an overall value assessment and make the overall decision. One reason to think this is true, even when people are presented with data in numerical form, is that there's a good bit of evidence that even when numerical data are presented to someone with number symbols, the brain represents the meaning of those number symbols in an approximate way, which is similar to the way in which internal representations of sensory magnitudes in the brain are equally imprecise. And this can be seen fairly directly from studies that look at the kinds of errors that people make when they have to respond to number symbols rapidly, but also when they have to give a response to information that they were presented with using symbolic representation of numbers, but after a delay. And so the Dehane and Marcus paper is an interesting example of this, where people were given price information and then they have to recall prices later. And the errors they make in recalling the prices with a delay look a lot like the errors in noisy sensory perception. I'm going to show you some examples here of errors in responses to numbers presented symbolically when the response is rapid. This is from a recent paper by Kerry Friedman and Salvo Nunari from earlier this year. They report an experiment where subjects have to indicate quite rapidly whether a number that's shown them is bigger than 55 or less than 55. And of course, that's not a hard problem if you get to think at all about it, but they have to answer very quickly, and so they don't always get it right. The numbers are being presented symbolically. They're always two-digit Arabic numerals. We call them Arabic numerals. I think they really probably came from India, but anyway, we call them Arabic numerals in the US. The degree of difficulty of quickly seeing the correct number seems to depend not on the appearance of the number symbol, but on how close the meaning of the symbol is to the number 55. It's not how much it looks like 55, but how close it is to 55 in its meaning. So here's a figure from their paper. I want you to look at the red data. I'll talk a little later about what the blue data are. But I want you to look at the data plotted by the red circles. This is the high volatility condition of their experiment, where one sees the effect more clearly. What's going on? Theta on the horizontal axis is the number presented to the subject. They have to quickly say whether that number is bigger than 55 or less than 55. The vertical line in the middle is if it were exactly equal to 55. And in the top of the figure, what you see is the probability of the subject giving the right answer. And you see they get it right a lot of the time, 90% or more of the time mostly, but they get it right more of the time when the number is significantly below 55 or significantly above 55. When it's not too different from 55, they're not getting it right as much of the time. And if you look in the left of the figure, as the number gets bigger and bigger, closer to 55, the probability of a correct answer is getting smaller and smaller and smaller. It's as if the precision with which they recognize what that number is, whether it's bigger or smaller than 55, is getting worse as the actual closeness of the meaning of the number symbol to 55 becomes smaller. If you look in the bottom panel, it's plotting the response time, and you again see response times are longer when the meaning of the number symbol is closer to 55 than they are when it's further from 55, either further below or further above 55. So this is suggesting that the fast decision is based on an internal representation of the meaning of the number system, of the number that's presented, which seems to be imprecise in a similar way that perceptions of sensory magnitudes like lengths of lines and tilts, sizes of angles, and so on, exhibit a similar imprecision. Okay, so what this suggests is that this imprecision is in the representation of the meaning of the numeral, not imprecision of the actual perception of the original number symbol. Okay, so that's the hypothesis I want to talk about. Something you might be wondering is, well, does it matter whether the noise occurs early in the encoding or retrieval of the information you were given about the description of the problem, as opposed to only coming in at the comparison stage? You might think that these hypotheses would predict basically the same behavior. You might say, well, okay, you might assume that people recognize the value of the options perfectly, but when they try to compare the two values, noise gets added in and they make an imprecise random decision. Or you might say they don't recognize the characteristics of the option precisely. Noise comes in how they're processing the description of the option, so they end up making a noisy choice. But can you tell the two things apart? You might think those might be observationally equivalent. So I want to talk about 3 ways in which one can get different predictions from this hypothesis of early noise, and then an optimal decision rule conditional on the noisy representation of the original information, as opposed to what those models that I presented earlier, those different models of late noise, would predict. So the first prediction that's different is that from this hypothesis that the information about the problem is encoded with noise, and then an optimal decision is made conditional on that noisy description of the problem, that can lead to biases in the estimation of the value of the choice options that are made, even when they're made optimally, based on this noisy encoding of what the subject was told. Those estimation biases can furthermore change across contexts depending on the frequency distribution of different items in a given context. So the same exact description of the item can result in a different average bias in the perceived value of the item, depending on the frequency distribution of different characteristics of items, say in a given experiment. So even with the same noisy encoding of the given information, the distribution of possible posterior beliefs about the value of the item can be different if those posterior estimates are formed conditioning on different prior. So the idea is the estimate, an optimal estimate of the value of the item based on noisy information, is going to take into account the noisy internal representation of what you were told about the item, but it should also depend on your prior over what kinds of items you're likely to be encountering in this experiment. In a different environment with a different distribution of items being encountered, the prior should be different, the posterior distribution should also be different, so the biases in the estimated value can be different. This is something that's been observed for a long time in perceptual domains, that there are biases in estimates of sensory magnitudes, and that those biases can be different for the same exact stimulus. The average bias in the estimation of the magnitude of the stimulus can be different depending on the frequency distribution of stimuli that are presented. A name for this phenomenon in the psychology literature that goes back to a paper by Harold Hollingworth back in 1910. He called this the central tendency of judgment. He pointed out already back then that one observed the same kind of pattern of bias in many different sensory domains. What he was talking about was the idea that when one presents the subject with different magnitudes, say one of his experiments involves showing them squares of different sizes. So the subject is shown a square, and then it's taken away, and then the subject has to produce an estimate of how big the square was that they were shown. And depending on the distribution of different sizes of squares that they're shown in the experiment, the bias in estimating the size of a given square changes. What he observed was that the smaller squares were overestimated on average in their size. The bigger squares had their sizes underestimated on average. Where you switched from being a square that would be overestimated to a square whose size would be underestimated depended on the distribution of sizes used in the experiment. And that dependence on the distribution of sizes in the experiment is what he called the central tendency of judgment. This is an example of that from a more recent paper. This is a paper by Mehrdad Jazieri and Michael Shadlin, published in 2010. In their experiment, they're presenting subjects with time intervals. So the subject hears 2 taps, and they have to then reproduce a time interval that's as close as possible to the time interval that the experimenter presented to them. So they have to make 2 taps with the same distance in time between them as the interval that they were shown. Okay, so what's being plotted on the horizontal axis is the length of the interval produced by the experimenter in milliseconds. On the vertical axis, the different dots are different lengths of time of the time intervals produced by the experimental subject, also in milliseconds. It won't surprise you that there's randomness in the subject's responses. They can't exactly do it. So for any given point on the horizontal axis, you see a range of different dots on the vertical axis. The more interesting thing is that they don't get it right on average. You don't have a distribution of dots that are on the diagonal. On average, the solid dots here, the big dots, are showing you the mean of each of those distributions. And what you see is for some time intervals, the average response, or even most of the responses, are longer than the actual time interval was. For others, most of the responses are shorter than the actual time interval was. And one observes this thing that Hollingworth had already reported, which is that, say, on the day where all of the time intervals were 850 milliseconds or longer, those are the red data. The red dots are for that day's session. And what you observe there is that when the time interval is 850 milliseconds or 900 milliseconds, on average, the subject estimates the time interval as longer than it really was. When it's instead on the order of 1200 milliseconds, the subject estimates the time interval. It's shorter than it really was, so the long intervals are underestimated, the short intervals are overestimated. But the interesting thing is that where you cross from overestimation to underestimation isn't just a function of the time interval presented to the subject. The exact same time interval, say it's 850 milliseconds, might be overestimated on average, or it might be underestimated on average. On the day when 850 milliseconds was the shortest time interval, it was almost always overestimated. On the day when 850 milliseconds was the longest time interval, it was on average underestimated. On the day when 850 milliseconds was almost right in the center of the range of values used in the experiment, then the average estimate is almost exactly right. Okay, so that's the central tendency of judgment. Here's a figure from another recent paper by Federica Petschner and her co-authors, showing that there are similar patterns in various sensory domains. So estimates of distances, estimates of angles, estimates of time intervals. One observes this same kind of context dependence of the bias in subjects' estimates of these sensory magnitudes. Okay, how can we explain that as following from this idea that the objective reality is encoded in the mind of the subject with encoding noise, and then they make a decision, they give a response, which could actually be an optimal response, conditional on having to be based on that noisy representation of the stimulus. So we can model this in a simple way. Suppose the true stimulus is a magnitude x, that's some real number, and suppose that in this experiment, x is drawn from a prior distribution, which I'm modeling as a normal distribution with a mean of mu, a variance of sigma squared. So I'm going to use the mathematics of normal distributions, which many of you will be familiar with. That's going to be our prior distribution. Suppose that this stimulus x has a noisy representation in the brain of the decision maker. We're going to have a summary statistic R for that noisy pattern of neural activity. And that R is a real number, but it's drawn from a Gaussian distribution conditional on what the x is. So conditional on the objective feature of the stimulus, say the length of the time interval, the internal representation R is random. It's drawn from a Gaussian distribution with mean x, but a variance mu squared, which is independent of what the true x is. So now we can ask what would be an optimal estimate of x if the subject has to produce their estimate based on this internal representation in their head, based on the R. And you have to say, well, what do I mean by optimal? The calculation I'm going to report here is what the estimate would be if it had to be based on R, and the decision rule minimizes the mean squared error of the subject's estimate. Okay, so that's an easy calculation in this case, because I've assumed these normal distributions. So the joint distribution of x and r is a bivariate Gaussian distribution. We know how to calculate the minimum mean squared error estimate. Some of you are going to recognize this as a linear regression problem. And that minimum mean squared error estimate, x hat, is going to be the conditional mean of x, conditional on r. It's going to be a linear function of r given by this formula on the slide, where the coefficient beta is a quantity between 0 and 1. So it's the slope of that regression line. It depends on the ratio of sigma squared to nu squared in the way indicated here. So conditional on the true stimulus magnitude x, the subject's response, x hat, predicted by this model, is predicted to be random, right? For a given x, the response x hat will depend on r. R, though, is random, conditional on X. So X hat will be random. The response that's observed will be random, conditional on the properties of the stimulus. It'll have a normal distribution, conditional on the stimulus, because X hat is a linear function of R. R is normally distributed. So X hat is normally distributed, conditional on X. We furthermore know what it'll be on average. The mean, which is also the median of this normal distribution, is easy to calculate. R is a normal distribution with a mean of X. X hat is a linear function of that. So X hat is a linear function, is on average a linear function of X, given here at the bottom of the slide. Okay, so the average observed response, conditional on the true stimulus X, should be this function of X. What does that imply? Something to observe about this simple model is it predicts that X will be overestimated on average for small x, because the beta is less than 1. So for small enough x, the average of X hat, conditional X, is going to be less than the true X, but it'll be overestimated for all large enough X. Specifically, it should be overestimated if X is smaller than mu, underestimated if X is bigger than mu. Where you cross over between overestimation and underestimation depends on mu. Mu was the mean of that prior. So it depends on what the prior distribution was. If we shift the mean of the prior distribution, we should shift the crossover point. That's exactly what was going on in these different experiments. The different experimental sessions have different average values of the stimulus in that session, and the crossover point correspondingly shifts. Okay, so that's an illustration of how this kind of model of optimal decision-making based on a noisy internal representation can give you this kind of bias, and specifically context-dependent bias captured by the central tendency of judgment. Okay, so you could also get random responses in an experiment like this under the hypothesis of late noise in the way I explained it before. You could say, well, okay, suppose the subject recognizes perfectly what the situation is. So they know the true X, they know their loss function, they know how much of a loss they'll suffer if they report a value X hat that's different from the true X. They know that quadratic loss function, but suppose their response is not the one that minimizes the loss function. It involves noise. Say their response is the desired response plus some random noise. We might justify this as comparison noise. They can compute correctly the loss associated with giving different responses X hat, but they make a noisy comparison of those different losses and end up making a random response. Okay, so we could explain a random distribution for X hat that is random, conditional on X. With this explanation, there's no obvious reason for that pattern of bias to expect X hat to be overestimated for small x's and underestimated for large x's. But even more importantly, there's no reason for the crossover from overestimation to underestimation to shift depending on the prior. Under the kind of model I was just sketching where the noise is comparison noise, you should expect the distribution of responses X hat to be the same function of X, regardless of what distribution X is being drawn from in a given experimental session. That's not what we see. Okay, a second reason why these two kinds of models, in fact, can give different predictions is if we consider the predicted consequences of changing the amount of time pressure that the subject is under. So in the case of the model of comparison noise, it's not obvious that time pressure is relevant. It certainly shouldn't change biases. Instead, though, if we imagine we have early noise, and specifically if the internal evidence about the decision problem, the decision is going to have to be based on, is modeled as a stream of noisy signals, like what's assumed in the drift diffusion model that I described before, that can also explain how decision time varies with the decision problem. We suppose the decision that is going to have to be based on a stream of noisy signals, which are noisy readings of what the relative values of the two options are, then less time for making the decision should mean less time for collecting additional signals, less time for observing this stream of random evidence. It should make the cumulative evidence that the decision is based on noisier. Bayesian decoding of this noisier internal representation should then mean not just that the estimates provided by the subject are more variable, but that there should be a larger average bias in the subject's valuations. So if we go back to our model of noisy coding here, you notice that if I assume that time pressure makes this nu squared bigger, nu squared is the encoding noise, the early noise in this process. If time pressure makes nu squared bigger, then when I go down to my value of beta for a given prior, amount of prior uncertainty, a bigger value of nu squared is going to make beta a smaller fraction of 1. Smaller beta is going to mean more bias in this formula at the bottom of the slide. So the bias is going to get stronger if we increase time pressure, according to this model, whereas under the model of comparison noise, there's no reason for bias that would be affected by the degree of time pressure. In a recent paper of mine with Rafa Polania and Christian Ruff, we do an experiment where we solicit valuations of food items from the experimental subjects, and we also have the subjects value the same food items, both under more time pressure and under less time pressure. And we find that the effect of more time pressure is not just that their reported valuations become more random, but that the average valuation of a given item changes systematically with the time pressure. It changes in a way that's consistent with the idea that there's a bias in the subject's estimate of how much they like that item that is consistent with this model of Bayesian decoding of a noisy internal representation of the item's values, where the noise in the internal representation is increased with greater time pressure. So this is showing you the nature of the systematic change in people's reported valuations of the same food items in response to time pressure. On the horizontal axis is the different food items rated from least preferred to less preferred, according to the average rating of that item by the experimental subject. So for a given experimental subject, we're rating from between 0 and 1, the least liked to the most liked item, according to their average rating of the items. On the vertical axis, there's a measure of the difference between how much the subject rates a given item under time pressure relative to their rating of the item when they have more time to produce their rating. So a positive value on the vertical axis means they value the item more when forced to give a quick decision than when they spend more time. A negative value means they value the item less when they have to give a quick decision. The overall slope you see in the figure is a downward sloped relationship. The most positive values for the least liked items over on the left, the most negative values for the most liked items furthest over to the right. That downward slope is like the bias I was showing you in those perceptual experiments, where lower values are overestimated on average and higher values are underestimated on average. So it's exactly like Hollingworth's central tendency of judgment. If that bias exists and the bias is made stronger by time pressure, what you should expect is then for the least valued items, more time pressure increases their overestimation. For the most liked items, more time pressure increases their undervaluation. So you should see positive value on the vertical axis for the least liked items, negative value on the horizontal, on the vertical axis for the most liked items. That's exactly what we see. Now, there's something more complicated occurring in the middle of the figure. We actually have the sign of the relationship changing sign. We go from stronger, increased value for time pressure to decreased value for time pressure to slightly increased value again, then to decreased value again in that so-called repulsion zone. In the middle of the figure, that's actually consistent with a model of optimal decoding of a noisy internal representation if we assume that the noise in the internal representation is not the same for all of these food items. And we show in our experiment that there is evidence of differential noise that we can measure by having the person rate the same item more than one time and seeing how consistent their ratings are. And in our model of Bayesian estimation of the value with the noise in the internal representation different for the different items, we get this more complicated pattern of bias shown in the left figure in this slide. So what is being shown in that left panel is the theoretical prediction of the model of Bayesian estimation of the value of the item based on encoding with noise of the value of the item. This particular model with inhomogeneous encoding noise that we fit to our model The black line is the predicted bias. Now, the estimated value different from the real value. Estimated bias in the valuation of the item in the case that the subject has 2,600 milliseconds to make their decision. That's the black line. The predicted bias when they only have 900 milliseconds to make the decision is given by the red curve. So what you see here is that there's bias in both cases. Even when they have the 2,600 milliseconds, the model predicts some bias, positive bias for the least liked items, then it becomes negative bias for things that are liked less than average but are not disliked as much as the least liked items, becoming slight positive bias for things that are liked more, and then negative bias again for things that are liked the most. With time pressure, you go from the black curve to the red curve, all of those biases become stronger. So now the curve has the complicated shape of starting positive, going negative, becoming positive again, coming negative again, but they're bigger swings in the curve. Now, if we ask about the difference between the two predictions, that's the difference we should see when the subject rates the same item, both under more time pressure and under less time pressure. The difference in the predicted biases is the blue curve over at the right. That predicts the kind of pattern that we actually see in the experiment. So this is all consistent with this kind of model of optimal estimation of the value of items based on a noisy encoding of what the subject sees on the screen, the item that they see on the screen and what they know about that item being by hypothesis encoded with noise. Other ways of manipulating encoding noise can also influence valuation biases. And there's an interesting example of that in this paper by Anke and Graeber that I've already mentioned once. So in their paper, they're interested in having subjects value simple lotteries, as I told you before. So they elicit from the subject what certain amount the subject says would make them indifferent between that certain amount and the lottery that the experimenter has described to them. The lottery promises some amount X with a probability P, and with probability 1 minus P, you're going to get 0. What they want to look at is the ratio of the certainty equivalent indicated by the subject to the value X that the lottery pays off, if it pays off. This ratio of certainty equivalent CE to X varies, of course, with the probability of the payoff. It's higher when the probability of the payoff is higher, as you would expect, but they're interested in whether the ratio of CE to X is the same as the probability P, as it should be for a risk-neutral decision maker, or not. And what they find is that the average certainty equivalent as a ratio to X is actually bigger than P for small p, but smaller than P for large P. And that's true both when X is positive, meaning we're talking about random gains, and when X is negative, meaning we're talking about random losses. That pattern of risk attitudes varying both whether it's a gain or a loss and whether it's a small probability or a large probability is a famous finding of Tversky and Kahneman, their so-called fourfold pattern of risk attitudes. So that's not the novelty of the paper. That's replicating a very famous finding in behavioral economics. The interesting thing, though, about Anke and Graeber is that they can manipulate on the assumption that this is coming from cognitive uncertainty about the description of the lottery. They can manipulate that degree of cognitive uncertainty. So what's the hypothesis here that they're interested in? They're interested in the hypothesis that these biases, these fact that the ratio of the certainty equivalent to X is not exactly the true probability, comes about because the subject's decision is being based on a noisy internal representation of that true probability. If we suppose that the true probability is in fact being represented with internal noise, then under the kind of Bayesian model that I just presented, the estimate of P conditional on the noisy internal representation should be biased toward the prior mean. In Anke and Graeber's setup, the prior mean is 50% because they have a symmetric distribution of probabilities around 50% used in their experiment. So that's the prediction, that you should behave like the probability is closer to 50% than it really is. That would explain overestimation, apparent overestimation of probabilities when they're less than 50%, apparent underestimation of probabilities when they're bigger than 50%. Now, the thing that is interesting is not just that they can explain Tversky and Kahneman's pattern, but that they can show then experimentally that there's something promising about this explanation. which is that they can manipulate the degree of noise in the internal representation by presenting the information to the subject in different ways. So they have a version of the experiment where they tell the subject what P is. They say this will pay off with 75% probability. That's the simple treatment. They have another treatment where they present equivalent information in the form of a compound lottery. They say there's a certain probability of getting one of various different lotteries, which will pay off with different probabilities. The compound lottery implies a 50% overall probability of getting a non-zero payoff. So it's mathematically equivalent, but they present the information in a more complex form. Their hypothesis is that the internal representation of the information is more noisy. The subject is more uncertain about what the true value of P is when the information is presented in the mathematically equivalent but more complex form. What they show is that that increases the bias in the subject estimate of the certainty equivalent of the lottery. Okay, so here's their data. There are two different experimental treatments, blue and red. Blue is when they tell the subject the number P, they directly tell it to them as a number. Red is when they present them with a compound lottery, which is equivalent to that simple lottery. In both cases, you see this fourfold pattern of risk attitudes. Risk neutrality would be the ratio C over E to X should fall on the diagonal line. Gains are shown in the top half, losses are shown in the bottom half. You should in both cases be on the diagonal if you're a perfect risk neutral decision maker. What one sees is that with gains, but probability P is high, you're below the diagonal in the upper right, you're above the diagonal in the upper left when it's gains, but the probability is less than 50%. Similar pattern with losses, but with the signs reversed in the bottom part of the figure. But the interesting thing here is comparing the blue data to the red data. The red data increase cognitive uncertainty by hypothesis. We're presenting the information about P in a more complex way. And what you see is that in almost all cases, that bias relative to risk neutrality is increased. Whatever the bias is, it's increased by presenting the data as a compound lottery rather than a simple lottery. So that suggests that the biases are indeed produced by cognitive uncertainty in the representation of the probability, as was being hypothesized. Okay, the third difference between these two models of randomness of choice that I want to talk about is that the two views also have different implications about the consequences of randomness in choice for strategic interaction. So far, I've only been talking about single decision problems of an individual decision maker who is told what the payoffs are from doing different things. But in experimental games, it's also commonly observed that subjects' play appears to be a random function of the payoff matrix that the players are told. And this randomness, I mean, I shouldn't surprise you if you believe what I told you before about randomness of subjects making individual decisions about problems that are completely defined to them by the experimenter. But it particularly matters in strategic situations because if this is true, if a decision maker's decision is random, even relative to what they understand about the payoffs in the situation, then that's going to particularly complicate strategic decision making because it's going to limit the ability of players to predict what the other players will do. Even if the payoff matrix of the game is common knowledge to both of the players, it's going to be complicated to predict what you think the other player should do if you know their behavior will be a random function of what they've been told. The most common way of introducing this randomness that people in experimental game theory have been used, again, this has been discussed for decades already. There's a very well-known approach to addressing this, the idea of quantum response equilibrium proposed by McKelvey and Palfrey back in the 1990s. They proposed this as a simple generalization of the classic Nash equilibrium concept for predictions about behavior in simple non-cooperative games. Okay, so what is a quantum response equilibrium? Two things have to be true. The second bullet point is the simplest. The expected value that the player assigns to a given action A is going to be based on a correct understanding of the equilibrium behavior of the other player. The behavior of the other player is going to be random, but game theory, even with Nash equilibrium, allows for random play. given the random play and equilibrium of the other player, there's a correct expected value of a given action to the first player. And that U of A that's used as an input to the decision of the first player is the correct expected utility of action A, given the equilibrium behavior of the other player. But the first bullet point now, instead of assuming that each player's action is they choose with certainty the action with the highest value U of A, if one of the actions has a higher expected payoff than any of the other actions, instead of that normal assumption of a best response given other people's strategies, there's a random comparison error of the kind assumed in, say, in an additive random utility model. So one uses a model like the model of individual decision making that was random that I talked about at the beginning of the lecture and plugs that into the model of choice in a non-cooperative game. And this is the proposed equilibrium concept. It replaces deterministic best response with this random comparison error, but the values that we plug into that softmax function are the correct assessment of the expected utility of the different actions given the equilibrium behavior of the other player. So this idea has been successfully used to explain the way observed play in various kinds of non-cooperative games differs systematically from the predictions of Nash equilibrium in various kinds of experiments. Gorey, McKelvey, and Palfrey have a nice book on quantum response equilibrium published in 2016 that summarizes a lot of that experimental literature and shows the usefulness of this concept. But what I want to ask is it obvious that that is the right way then to introduce randomness into the way people are predicted to play games? It does get some things right, at least as relative to Nash equilibrium. It's a definite improvement. But we could also get randomness into predicted play in games by supposing that people encode what they're told about the game with noise, as we've been discussing, and that they play optimally given their noisy internal representation of the information they were told about the game. And that kind of model does have importantly different predictions than quantum response equilibrium. So I want to illustrate that using the discussion of the paper by Friedman and Nunari that I've mentioned before. Their paper is actually not about errors in people's perception of numbers. It's a paper about non-cooperative games. This is actually now the real point of their paper is to discuss how cognitive imprecision makes predictions about how people will play a coordination game. And so this is the kind of simple coordination game that they discuss. There are two players. They each have two strategies. As usual, we use a box to represent the payoffs to the two players for their two strategies. Each has a strategy, not invest or invest. The two columns for each column player, the two rows for the row player. The two payoffs for each pair of actions are given in each box. And as usual, the first number is the payoff for the row player. The second number after the column is the payoff for the column player. So what this game payoff matrix says is that for either player, if they choose not to invest, they get some payoff theta, which is a parameter of the game, with certainty. They know what will happen if they don't invest. It doesn't depend on the other person. They get theta. If they invest instead, their payoff depends on what the other person does. They get A if the other person doesn't invest. They get B if the other person does invest. And we're going to assume that B is bigger than theta, but A is less than theta. So if the other person invests, it's better to invest than to not invest. If the other person doesn't invest, it's worse to invest than to not invest. We'll suppose that if we suppose the payoffs are common knowledge, then we can analyze the Nash equilibrium of this game. And as well known in this kind of coordination game, you have multiple Nash equilibria. Even if you look at Nash equilibria with pure strategies, no randomization, there are two of them. You can have a Nash equilibrium where both don't invest. You can have a Nash equilibrium where they both invest. Quantum response equilibrium makes different predictions, of course. It makes play necessarily random in that game. Even if you have an equilibrium where your opponent is highly likely to invest, you are not going to choose to invest with certainty. You're going to follow that softmax function, which implies there'll be some probability of not investing, even if your opponent invest with a very high probability. And even if your opponent invests with a very low probability, there's still some positive probability that you will invest. Okay, so that comes out of the randomness of the softmax function. But this randomness that's introduced by quantum response equilibrium doesn't eliminate that equilibrium multiplicity that I was talking about, at least if the randomness is only moderate. There's still going to be both an equilibrium in which each player invests with a high probability because the other one invests with a high probability, and an equilibrium in which each invests with a low probability because the other one invests with a low probability, as long as the degree of imprecision is not too great. So that temperature parameter is not too big. One is going to get a unique equilibrium in the model only if you introduce a sufficiently large degree of randomness, and that doesn't fit that very well with what's actually observed in experiments. How do you analyze this? To analyze the quantum response equilibrium, we can think of motivating the softmax function by assuming it's like a random utility model. So there's some expected value of investing for, say, the role player. There's a true expected value of investing given the equilibrium behavior of the other player. There's a true expected value of not investing. On a given trial, when the subject has to decide whether to invest or not, we're going to add random quantities epsilon and epsilon 2 to those two numbers. And on this occasion, the subject invests if epsilon 1 and epsilon 2 are such that this inequality holds. So we can work out the probability that the subject will invest as a function of the parameters of the game on the assumption that the epsilons are drawn from a Gaussian distribution with a noise parameter mu squared. We get this function for the probability of investing as a function of A and B and theta. Those were the parameters in the payoff matrix. As a function of this nu, which determines the amount of comparison noise. It also depends on P, the probability in equilibrium that the other player is investing. So we get a prediction that the row player, say, should invest as a certain increasing function of the probability with which the column player invests. We can get a symmetric equilibrium by asking for P to be a fixed point of this mapping. We want to ask what's the probability P of investing, such that if your opponent is expected to invest with probability P, this model predicts that you will choose to invest also with probability P. So we want the P, which is such that P is phi of P. The mapping phi of P depends on the parameters. In particular, it'll vary for fixing A and B. It'll vary as we vary the parameter theta. That's something that's often studied in coordination games like this, is how do the equilibria change as you change the value of that outside option, the value of theta. And the answer here is this equation can easily have multiple solutions for P. If theta doesn't have too extreme a value and the noise is small enough, in fact, you're going to get multiple solutions. And the reason for the multiple solutions, if we go back to the equation here that we're looking at the fixed point of, the function on the right-hand side, that phi is the cumulative distribution function of a standard normal distribution. So that phi, as you know, has a sigmoid shape. It starts out flat for very negative values of the argument. It becomes steeply increasing for values of the argument that are not too different from zero. It becomes flat again for larger positive values of the argument. Okay, so in the equation at the bottom of the slide, phi is a sigmoid function like that. The function of P, the function on the left is linear in P. So it's a straight line increasing function of P, and that straight line can cross the sigmoid function at 3 different places. Intermediate values of theta are the ones that will make there be 3 crossings as long as the sigmoid function is steep enough, which means as long as nu, the noise parameter, is not extremely large. Okay, so that there's some algebra here of that, but I've told you the intuition. Okay, so the model is not so different from the model with common knowledge, except it makes people's behavior more random. You don't have an equilibrium where you both always invest. Instead, it's an equilibrium where you both invest with high probability. But except for introducing a little noise, the qualitative predictions of the model, in predicting the multiple equilibria, and it being completely arbitrary whether people should settle on investing with high probability or not investing with high probability continues to be the case. The model with cognitive imprecision that Friedman and Lunari discussed instead gives qualitatively different predictions. In this model, the subject's, each player's decision is assumed to be based not on knowledge of the precise value of theta, but on a noisy internal representation of what they've been told about that parameter theta, the value of the outside option. Now, they might have cognitive uncertainty about many features of the game, but what Friedman and Lunari assume is that actually everything about the game is perfectly well known except theta. And they conduct an experiment where everything is always the same in each version of the game, except theta is different for different games. So they have the subjects play different versions of the game where theta is different. And because theta is different for different versions of the game that they're playing, that's why they suppose that there's more cognitive uncertainty about the value of theta. In the theoretical model, the decision is going to be made based on a noisy internal representation of what theta is for the game you're playing right now, rather than the true value of theta. This noisy internal representation has a probability distribution. It's given by a noisy signal SI, which is a transformation of theta, a linear transformation of the value of theta, plus Gaussian noise added to it, a mean zero noise term. The linear transformation, M of theta, is there to rescale this external state theta to ensure that the signal SI has a variance that remains within a finite bound. So they're assuming that the internal representations can only vary a certain amount. And so the scaling of theta in this noisy signal has to be changed so that the variance of S sub I remains within this finite bound. The noise in the epsilon terms is assumed to be some constant. It's independent of what theta is, and they're going to assume it's independent of the range of variation in theta as well when they end up varying that. Okay, so we can ask about what an equilibrium is like of this game. They show that it has the form of being a monotone decision strategy for each of the players, conditional on their noisy representation of the game. The noisy representation is just this S sub I. And in the equilibrium strategies, each player is going to invest if and only if S sub I, this is an error on the slide, it should be below a threshold, not that it's above a threshold. If and only if S sub I is below a threshold S star, the player invests. So they always invest if their noisy representation says that SI is less than the threshold, and they never invest if their noisy representation says SI is below the threshold. But because SI is random, the play of the two players in a given game, characterized by a given value for theta, is in fact going to be random as a function of theta. What is the S star? You can ask what the equilibrium value of S star should be. It should be the threshold that it's rational for a given player to use. It represents the optimal decision rule for that player, given the noise in their internal representation, and given the random play of the other player. That gives us a fixed point problem to solve for S star, because the optimal threshold S star for one of the players depends on the decision rule of the other player, which depends on what S star is for the other player. Again, we're going to look for a symmetric equilibrium because the whole game is symmetric between the two players. So we're going to find the S star that satisfies the fixed point problem. And what they show is that for any small enough omega, any small enough amount of cognitive imprecision, that's the noise in the internal representation, you get a unique fixed point S star. And so that is different from the prediction of the quantum response equilibrium, at least in the case of small cognitive uncertainty modeled the way it's modeled with quantum response equilibrium. Some of you will recognize that this result of a unique monotone equilibrium of this kind in the case of small enough noise is in fact a familiar result from what's called the global games literature, which introduces randomness into this kind of coordination game, usually not interpreted as cognitive imprecision, but is interpreted as noise in a signal that each of the players get about what the value of theta is. So in the kind of games that Carlson and Van Damme discuss in more general theoretical terms, and Morris and Shin apply to a model of currency attacks in a paper that's very well known in the international finance literature. In those global games models, it's assumed that there's a true theta, but each of the players gets noisy private information about theta, and their action has to depend on their noisy private information. And the result is that if the noise in the private information is has any small enough value of the noise parameter omega, you get a unique equilibrium for the game. That's the famous global games result. That result doesn't involve this rescaling of the m of theta function with the distribution of values of theta. But the more important thing is that the normal interpretation in that literature is that you are solving for the Nash equilibrium of the game. It's a game with imperfect information. It's because the players have imperfect information that you have the kind of solution and the random behavior that you get. This prediction of the global games type solution is more in accord with what's observed in laboratory experiments where people play games like this than the prediction of quantum response equilibrium. What one finds, Frank Heinemann and co-authors have a couple of interesting papers from back in the 2000s where they have people in the laboratory play games of this kind. They find behavior in which the probability of the crisis, where people don't invest, that's the crisis state in the model of bank runs or model of currency attacks. What they find is the probability of the crisis occurring in the laboratory seems to be monotonically related to the economic fundamentals, the true value of theta, in a way that's consistent with this unique solution under the global games assumption. And the quantum response equilibrium solution concept doesn't explain then why you would have a unique solution with that particular property. Normally, interpretations of the global games result, though, assume that it depends on the players having private signals about the fundamental, and that analysis implies that if there existed some public signal about the value of theta, the existence of the public signal should give rise to multiplicity again, as long as the public signal, if the public signal at least is sufficiently informative. Under the interpretation proposed here, the solution with people playing randomly isn't because they have to base their decisions on a private signal, which is noisy and uncorrelated with the private signals. The noise, that is uncorrelated with the noise in other people's private signals. Instead, under the interpretation that I'm proposing here, each of the players has an internal representation of the situation that involves idiosyncratic noise, because it's noise inside the head of that particular player. So they have to base their decision on the noisy internal representation of the game that they have. It involves idiosyncratic noise. It's not noise in the way the situation is described to them by the experimenter. And this idiosyncratic noise should exist even when the fundamental is publicly observable by everyone. So when the experimenter tells both of the players exactly the same thing about what the value theta of the outside option is. The noise is cognitive noise rather than a feature of what's visible about the world, as in traditional models of asymmetric information. This prediction that it isn't about the non-existence of a public signal that leads to the global games prediction fits with the finding in the work of Heinemann and co-authors that in their laboratory experiments, when they varied the amount of private information as opposed to public information that the subjects had, varying the degree to which people had to depend on private information as opposed to public information, didn't change their observed behavior very much. Our model, in fact, implies that that isn't what determines the nature of the randomness in people's choice, assuming that there's not a lot of noise in the available information about theta, and that seems to fit better, in fact, with what's going on. I guess I will skip this further discussion of a further difference between quantum response equilibrium and the cognitive imprecision model. What Friedman and Nunari go on to do is to show that theoretically, if the encoding of theta varies systematically with the distribution that theta is drawn from in a particular way, that also implies that the sensitivity of behavior to variations in theta should change depending on what the prior distribution for theta is. That also is not predicted by quantum response equilibrium. They show experimentally that when they change the distribution of different values of theta used for two different pools of subjects, that there is a change in subjects' behavior. And that's why they were actually interested in the effects of changing the variability of the numbers presented to people on the accuracy of the perception of the values of numbers. They apply that idea to their non-cooperative game, and they have people playing the same games. Theta on the horizontal axis are the same games for each value on the horizontal axis in these two conditions, but one group of subjects have the values of theta are drawn from a bigger range, not just the range shown on the slide here. And in the other low volatility condition, there's a group of subjects that only have values of theta between 47 and 63. And what you see is that for the subjects for whom theta is always between 47 and 63, their behavior varies more sharply with variations in theta than in the case of the other subjects. Again, there's a simple interpretation of this in terms of the model of cognitive imprecision, which I don't think I have time to talk further about. Also, changing the variability of theta across different versions of the game changes the average response times of the two pools of subjects, again, consistent with that model of endogenous change in the nature of the noisy encoding of the information about the game when one changes the range of values of theta that have to be encoded. Okay, so to wrap up today's lecture, I think there are important advantages of having a model of imprecise cognition that's based on noisy internal representations of the data that are available to the decision maker and that define the decision problem that has to be solved. In saying this, I don't mean that there might not also be comparison noise or control costs of the kind that I talked about at the beginning of the lecture, but it doesn't seem that those are the only sources of noise in people's observed choice behavior. Why I'm interested in this, noise in internal representations provides an explanation, not just for the fact that people's choices seem to be random, conditional on the true characteristics of the options presented to them, but it can also provide an explanation for systematic biases in the average evaluations of the choice options. And I'm going to talk more in the remaining two lectures about this issue of systematic biases and how people value things following from randomness of internal representations. I'm going to talk about how this can provide an explanation for apparent departures from predictions of rational choice theory in a couple of contexts. In lecture 2, I'll talk more about some anomalies connected to choice under risk. And in lecture 3, I'm going to talk about evidence that the way people seem to subjectively value things varies with the context in which they encounter that particular description of the items that they can choose. So that's where we're headed in the remaining lectures. Thanks. If there's still a couple of minutes, maybe.
Yes, we do have. Thank you. Thank you. Very, very enthralling exposition to the broad literature, and I think the other two lectures will make it more clear about how to apply them. We have time for maybe 2 minutes for a couple of questions. So Dibendu had a question typed in the chat box earlier. Dibendu, you want to unmute yourself and ask it? Dibendu?
Yeah. Okay. Can you hear me?
Yes, I do.
Yeah, Michael, that's a fascinating talk. I think the questions I posed were a bit of based on the early part of your lectures, but you tried to move into different directions. But I want to actually flag 2 points. So, of course, you tried to argue that under uncertain situations, how human brain process that actually produce biased results. That's fascinating. Actually, this is actually coming over and over in recent years. But if you look at also a couple of old school of thought, let's say pure Pavlovian kind of argument, Pavlov, who is to say that the human behavior is to some similar to the animals. The behavior is much more sticky, and you can predict, even under certain noisy circumstances, you can predict their behaviors. This is one set of literature. Another set of literature who also works on the philosophy to try to say that people behavior is highly driven by the ideology, culture, where they believe, where they live, something like that. So I think this kind of model, entirely undermine those sort of school of thoughts. I mean, is there any particular reason, or do they also pass in somewhere in the systems? So I mean, basically, this is my precise question.
Well, so I'm certainly not going to talk about all of these things, I mean, in these lectures, because I'm going to be talking about some relatively simple kinds of choices and how observed choices depend on the features of the precise situation that experimental subjects are told about. But what I want to point out, I mean, I think there's a connection between the research program I'm talking about here and those broader themes, which is what I'm going to try to convince you of in these lectures is that even if one supposes that the way people respond to a situation is through a decision rule, which is actually very well adapted to the type of decision problem they're facing, that with sufficient experience, perhaps they've learned to respond in a very good way, if that response has to be based on a noisy representation of what the situation is on a particular occasion, then other complications will have to come in, even if they're responding optimally, subject to basing their decision on this noisy representation of the decision problem. And I mentioned the prior, right? One of the things that came up already several times is that the prior then also becomes a determinant of predicted biases in the way the subject will evaluate their options and what they will be more likely to do. And if you ask, what did I mean by the prior? Well, I talked about some situations where experimenters could change what the prior should be by changing the set of games that the same person plays on different trials in the same experiment. But of course, if you ask, wait a minute, is a prior just something the experimenter gives to the decision maker? I tell you what your prior is. I mean, come on. I've showed you how experimenters can try to change what the prior ought to be by changing what they know the subject has been exposed to. But of course, people probably bring priors that come from other things in their life too. So you mentioned, cultural teaching and ideologies. And of course, those are things that affect people's priors. And so once we explain that not just what they've been told directly in a decision problem matters, but also the priors they bring to the interpretation of what they think might be going on in their head. As soon as those priors become relevant, then other things like ideologies and cultural background can indeed potentially be shading those priors and therefore shading their decisions. Also, other things about your previous experience. And so you mentioned things like the literature on conditioning by experience in psychology, where there's been a lot of study about how the likelihood of animals or people making particular responses can be shaped by the things they've been previously exposed to. But again, where do priors come from? They have to be some kind of reaction to your previous experience. So many aspects of previous experience may be systematically shaping behavior. So I'm not going to be talking about all of those things, which are too much for me to do in just these 3 90-minute lectures. But I think the approach I'm suggesting opens the door to also thinking that those other things may well be relevant. And as you said, there is some experimental evidence indeed suggesting that other kinds of determinants of behavior can be shown to matter.
Yeah, done. Thank you. I'm looking forward to hear 2 more lectures.
Yeah. So just to add to that, Michael, probably that theta, the temperature parameter, would be influenced by all kind of culture and stuff like that, right? So the internal.
Well, that's right. So again, I talked about experimental manipulation of it. Some ways that we changed the time pressure. Enke and Graeber presented information in a more complex way. But again, that didn't mean that we, the experimenter, could just give people their theta. The theta obviously depends on features of people. And indeed, there are experiments, that show that the value of theta seems to be affected by things like people's familiarity with dealing with numbers. When we're talking about, the accuracy of number representation, people with more experience dealing with numbers seem to have a lower value of theta, and people who are less numerate seem to have a higher value, and so on.
Okay, so we have to wrap up. We are running on a tight schedule and the parallel sessions are due now. So thank you very much, Michael. We just look forward to the other 2 lectures, which are going to give us much more of this. And I'm sure others will join us also. The next lecture by Michael is, this evening, Indian Standard Time. What is the next lecture time, Dibyendu?
6:30.
Yeah, 6:30 Indian Standard Time. And we look forward to seeing you again, Michael. And now, those who want to have a one-to-one chat with Michael after the lecture series, please register for the breakout session for 10:15 p.m. Indian Standard Time today. Thank you very much, Michael. See you for the next lectures. Bye.
I'll see you all later today.
Yeah. Bye. Bye. Thank
Bye.
you. Thank you, everybody.